Hello, thank you for tuning in. My name is Rakibul Hasan, presenting our paper Understanding Utility and Privacy of Demographic Data in Education Technology by Causal Analysis and Adversarial-Censoring. This is a joint work with Mario Fritz. So, education technologies can be defined as technologies used in educational context, and they are pretty much everywhere in various forms. For example, Canvas is one of the most popular learning and management systems used in higher educational institutes mostly. Google Classroom provides complete virtual classroom management solutions that doubled its user base during the pandemic. ClassDojo is also one of the most popular applications for monitoring children in school. It rewards kids for quote unquote good behaviors and punishes them for bad behaviors. eHolpass, that's my favorite. So it tracks students' movements in campus buildings and hallways, including when they visit bathrooms. And jointly, all, these four applications have more than 230 million users. And here is a bigger picture. So it was estimated that the edtech market will exceed 341 billion US dollar by 2025, but the pandemic further accelerated that growth to more than 400 billion US dollar. And simultaneously, we are seeing an increasing number of privacy violating incidents. Many incidents involve data breaches, hacking, and so on, but a lot of incidents involve data abuses by edtech vendors or their business partners for profit. So the natural question is then, why so much data are being collected? And the reason put forward by edtech vendors and their partner institutes are building models to predict students' performance, or who among them will likely drop out from a course, or to recommend appropriate course, personalized books, and so on. So these models are trained using data such as how students interacted with learning management systems or online portals, their activities and movements, and even highly private data like their demographic and background information. So the claim is that such learning analytics will help student retention and improve the overall educational experiences. And these are seemingly novel causes. Although many scholars in education, law, and computer science argued that most of these technologies were not scientifically evaluated and may actually harm students. But even if these tools have the potential to be useful, the question we asked in this paper is, do they really need all this data? In this paper, we show that the privacy-sensitive demographic attributes such as gender, age, they are not really required to predict performance or dropout probability or any other outcome. So consequently, we argue against collecting such information. But we also found that such attributes can be inferred based on how students interacted with the learning management system. So we propose a method to prevent such inferences using adversarial censoring and constraint optimization. And we demonstrated our evaluated our methods on the Open University Learning Analytics dataset, which is one of the most widely used dataset in the research community. It contains data from more than 32,000 students, and the data types include students' interactions with online portal like visiting course pages, assignment submissions, taking part in quizzes, and so on. There are demographic data like age and gender, and historical data. So since most papers based on this dataset or other similar datasets used gender as an input feature to predict performance, we first wanted to test if gender correlates with course performance. And the answer was yes, we found correlation between gender and performance. So the next question is whether this association was causal. That is, if students' performance differed because they differed in gender, while everything else, such as their activities, their background, and everything, remained constant. So we want to find pairs of students who performed similar activities throughout the semester and had similar backgrounds, but differed only in gender. Let's say we have two sets of students who identify with X and Y genders, respectively. We embed these students into a vector space such that students who behave similarly were placed close to each other, and we paired the nearest neighbors. Then we again tested if gender was associated with course performance within these matched samples, and the association disappeared. This means if everything else remained constant, gender does not have any predictive value. By extension, whatever predictive value it had before, it was most likely due to the encoding of some demographic biases. But unfortunately, gender can be inferred from behavioral data. A very basic logistic regression model can predict gender with over 73% accuracy, which is 39% improvement over the Bayesian accuracy. A 3-layer deep neural net can increase the accuracy to 76%. And more sophisticated models will likely predict even more accurately. And the dataset we were using is much, much smaller than datasets collected by large edtech providers. So we want to find a way that will allow collecting or sharing this data, this kind of data for research purposes without risking students' privacy. So we have 3 sub-goals. The first one is to prevent inference attacks or inferring sensitive attributes. Second goal is preserving utility, which means allowing building these kind of predictive models. And the third goal is to identify a subset of the features that satisfy the first 2 conditions. So the final outcome is a small subset of the input features that can be used or that are enough to build learning analytics, but not to that they cannot be used to infer gender. And so the collected data can be shared with other business partners or research partners. So to achieve the first 2 goals, we applied an adversarial censoring technique. So similar to typical neural networks, we have our input features. They are fed into intermediate layers and then to the output layer that predicts performance. But we simultaneously predict students' gender. During training, the gradients are updated as usual to improve performance prediction at every iteration. But for gender prediction, we did the reverse gradient update. As a result, the model gets worse in predicting gender over time. To identify a subset of these features, we used a feature selection layer. So that was inserted between the input layer and the other intermediate layers. Let's look more closely at how this layer operates. So there are n nodes in this layer. N can be anything, any number. So all features independently enter into this node, and the node parameters were constrained to be either 0 or 1. That means features with associated parameter value 0 will simply be discarded. The nodes also have linear activation function. So that means each node's output is just a sum of all the input features that survive the feature selection process. So this property of the model may enhance its interpretability because by looking at how different features combined, we can get an idea, or education experts can get an idea of how collection of interactions create meaningful behaviors for better learning. So going back to the feature selection, this is the penalty function that we used in the feature selection layer. So observe that the penalty function is minimum when the parameter value is either 0 or 1. So now the good news is that using this model, we could prevent gender inference. You can see the performance prediction and gender prediction. Gender prediction accuracy is at the baseline level or chance level. For comparison, we trained 2 sets of models to independently predict performance and gender. You can see that the constrained model predicts performance with the same accuracy as other models, while bringing down the gender inference accuracy to the chance level. Now for goal 3, we want to know which features survived. We found that only 3 nodes had some non-zero parameters. All other nodes had all 0 parameters after applying the penalty function. So in those 3 nodes, only 6 unique features survived this process, and their combinations were passed to the subsequent layers. That means only 6 features are enough to predict performance while not risking students' privacy. So now we examine how generalizable and robust our approach is. In the paper, we provide cross-validation results over randomized data splits, as well as show how generalization of our approach to other settings and tasks. So, but very briefly, we follow similar approach to predict performance while preventing age group inference and to predict dropout probability of students while preventing gender inference. So these are very different tasks, but each time we obtain similar results. And all experiments were done hundreds of times with randomized initializations and trained test speeds. So these results provide the generalizability and robustness evidence of our approach. In summary, edtechs are already ubiquitous in many countries and will be the same globally in the coming years. Students, many of who are too young to consent for data collection or even to understand the consequences, will continue to be massively surveilled in the name of improving education. So in this paper, we demonstrated that learning analytics can be done while protecting privacy, but we need much more research efforts to close those invasive surveillance eyes before technologies take over education like many other social institutes. Thank you so much for your attention.